Welcome back, everyone. Today we'll take that vector and we'll apply it to the real world three-dimensional space. I showed you this the other day. Okay, we're going to use this notation, not this notation, but this orientation is what I meant to say. Notice here that the x, y, z axes, it doesn't really matter which way you put your x, y, and z's, right? It's all relative, right? What's on top, what's on bottom? Well, I guess it depends on where you're standing, right? Because we can do it any different way, we can have the y here, or the y here, x here. All this is doing is taking your x, y axes and laying it on the ground and then having the z shoot up and down. But for our class, we're going to do it this way. This way we're all doing it the same fashion. I think it's the easiest, and this is why. Well, you're already familiar with your positive x-axis and your negative x-axis, your positive y's and your negative y's. So we'll just treat the positive z's as coming out towards us and the negative z's as going away from us. Okay, that's a z. Everything else is the same, except instead of an ordered pair, which is an x and a y coordinate, we now have ordered triples. Triples. So instead of just an x and a y, we also have a z component. Okay, so there's our ordered triple. And we figure them out the same way too. You take, well, let's just say that we're going to have x1, y1, z1, comma, comma. And I'm going to let that be the origin right there. And then we're also going to have x2, y2, and a z2. That's a z. And that will be the coordinates for the head. Well, just like before, we did x2 minus x1 and y2 minus y1. We just need to include z2 minus z1. Sorry, my z's look like 2's. Remember what that does for us. It takes any vector in space, and when you do this to it, it is like translating it back to the origin, as if it were starting at 0, 0, 0. Okay? All right, well, that's that. Let's look at this example right here. Whoops, what did I just do? Undo. Now I'll just leave that line there. Worse things have happened. Now this one's already translated down to the origin. As you can see right here, it's starting at the origin and it's going up here in space. So that's 0, 0, 0, right? It's 0 on the x, 0 on the y, and it's 0 on the z. And this vector, well, let's figure out what that vector is doing. This one, I am going 5 units on the x, so it looks like my x coordinate is 5. And then we are going up 8 units on the y. And then we're coming out towards us, how many? 3 units on the z-axis, so it would be a 3. And if this was somewhere else in space, I would just be subtracting, taking the difference of my x, y, and z values like we showed you over here. But because we're just subtracting 0, you're going to wind up with this anyway. So that is the ordered triple for the vector in that example. Great. Now how do we find the magnitude? I want to know the length of it as well. Well, the magnitude, the way we did it earlier, with 2 dimensions, magnitude, was we took the square root of x squared plus y squared. All we do differently is we include the z component, plus z squared. Let's find the magnitude. Let's pick another color here. Was that peach? Let's try peach. I'm going to move that over there. That's fine. All right, well, if we plug in our values, I have 5 as my x. I have 8 for my y. And we have 3 for the z, which is going to give us 25 plus 64 plus 9. And when you add them up, it comes out to the square root of 98. That's not simplified. You can simplify the square root of 98, but for right now, that is the length of the magnitude. We'll talk about simplifying at a later date. Okay, that's how you find the magnitude. You know, other than that z component, there is no difference with doing operations with vectors. I'll show you what I mean. let's take two vectors, a and b, and we'll let a be x1, that's a 1, y1, and z1, and b will be x2, y2, z2. We're going to need a scalar, so why don't we call k, I don't know, pick a winner. Let's get crazy. Let's do 2/3. 2/3 is a real number. Okay. So if I were to ask you to add a and b, vector a plus vector b, it would be x1 plus x2, y1 plus y2, and this right here is the only difference. We have a z component, so we have to add our z's. I think we can do that. I'm not going to bore you. Subtraction is the exact same concept as we talked about. We just have the z component. So not only do we take the difference of the x's and the difference of the y's, but we do the same for the z's. z1 minus z2. Please be mindful again, subtraction is not commutative like addition is. So if that a comes first, my x, y, and z for a must come first. 8 minus 3 is not the same as 3 minus 8. Scalar multiplication. If I gave you k times a, well, here, let's do this. K was, well, here, all you're going to do is, you know what? I gave you a value for 2/3, but we're going to do an example with numeric values in a minute. Let's just say k is our scalar. So if I had k times a, well, what was a? A was x1, y1, z1. And I always forget my parentheses. You just distribute, like we did before. It would be k times x1, k times y1, and k times z1. Okay, now we'll do some examples, and we will utilize this value for k 2/3. Okay, well, we've already established, whoops, that's not it. We've established that our scalar is going to be 2/3, everyone's favorite fraction. I don't know, what do you want a to be? Maybe we'll throw in a negative there. So how about negative 2, comma 0, comma 4. And vector b, I don't know, 3, 1, negative 3. I just made it up. It really makes no difference. The math is the same. Addition. If I'm going to add a plus b, I have negative 2 plus 3, 0 plus 1, and the z values, 4 plus a negative 3, which is the same as 4 minus 3. Do your math, you're going to get 1 for the x, 1 for the y, and that was a coincidence. I didn't mean for that to happen. 1, 1, 1 was the addition. Subtraction. Let me just show you what I mean, and this time we'll do b first. If I were to do vector b minus vector a, well, b's first, so my b values must come first, because subtraction is not commutative. So that's going to give us a 3 minus a minus 2. That's 3 plus 2. I have 1 minus 0, and negative 3 minus 4. That value, the x comes out to be 3 plus 2 is 5. 1 minus 0 is 1. And a negative 3 minus a 4, don't forget, two negatives give you a bigger negative, negative 7. Scalar multiplication. If I said find k times b, we'll use b this time. Well, k was 2/3. Our b vector is 3, 1, negative 3. Let's distribute. You're going to get this. Now don't forget, you're just multiplying fractions. These are all over 1, so you multiply your numerators and denominators. So when you do this multiplication right here, you're going to get 6 over 3. 6 over 3 is the same as 2. When you do this multiplication, well, 1 times anything is itself. So 1 times 2/3 is 2/3. And when we do this one over here, 2/3 times that, that's going to give us a negative 6 over 3. Negative 6 over 3 is a negative 2. There it is. Ta-da! Now for those unit vectors. We no longer have just unit vector I on the x and unit vector j on the y, but we do have unit vector k on the z. I did mention that the other day. Well, I guess if that's the case, then we're not really talking about a unit circle anymore. That would create something like a unit sphere. Now, I'm using this picture because it's a nice representation of the spherical relationship here. But it also has these little vector e's. Don't get hung up with the Greek letters here. We'll save them for a rainy day in physics. But just understand here that if you have a unit vector on the x and a unit vector on the y and a unit vector on the z, that it's now going to create a sphere with a radius of 1. Why do we do these things? Why do we track direction and force of all these different things? Don't forget, the magnitude is the force. It represents the force. So the longer the vector, the more force. Okay, that's going to be a very important role in our word problems coming up, our applications. Well, here's one application. Water currents. We have a lot of boats going across the seas. We need to know the fastest route and the safest routes, and we want to avoid dangerous zones, too strong, all those fun things. And that's what vectors do. These right here are all little vectors in here, okay? And they show in each part the force and the direction of the water. You want to take your boat one way, you don't want to take a boat the other way. So knowing where the force, where the best routes are and the worst routes are, that's just one very simple application of vectors. Okay, let's take a vector in 3D space and rewrite it as it's the sum of its unit vectors. We will do this example. I am going to take this vector, 6 on the x, 8 on the y, 3 on the z, and we're going to write that as the sum of its unit vectors. Well, don't forget the whole concept here. Let me just move that. I need a different color. Okay, let's take this one right here. And if we apply those values, well, let me see. I'm going to use purple for the x. So this right here has a length of 6. Well, I showed you the other day how we could represent that as 6i. Okay, just revisit the last video on algebraic vectors if you don't remember that. Now, we could also take that and translate it wherever we want. So long as it has the same direction and the same magnitude, doesn't matter if it's there or there. What about the y's? Well, the y's will do in orange. Okay, so I'm going up 8 units on the y-axis over here. All right, well, that means that this vector going from the x-axis up the y-axis has a length of 8. And that would be written as 8j. And the z value, well, the z's will do in green. Okay, and there's a 3. So I'm going out 3 units on the z-axis. Okay. And again, we can translate that, whether the green arrow is there or there. It's going to give you a length of 3. And that would be written as 3k. If you need to draw vectors in 3-dimensional space, watch what I'm doing here. Let me go back to the orange one. Whether this orange vector is here, or if I translate it over here, again, as long as they have the same direction, the same magnitude, or if I moved it over here, or I moved it over here, either way, it's going to have the same direction, same magnitude. Same thing with the greens, whether I come out 3 units this way, or 3 units this way, or 3 units this way, they have the same direction, same magnitude. For the X one, well, whether the purple arrow is down there, or up here, or over there, again, same direction, same magnitude. If you saw what I just did there, I drew a rectangular prism. It kind of helps you when you're trying to draw these in 3 dimensions. I'm going out this many on the X, I'm coming out this far, I'm going up this way on the Y, and I'm coming this far out on the Z axes, which would put the head right around there from the origin. This is not a very challenging concept, but one more example, just to be sure. And again, orientation on this picture is a little different, but again, it's all perspective. So here, the x value is here, and the y is here, and the z is here. All they did here was they took your normal x-y axes and they flopped it on the ground, and they're treating the z as shooting up and the negative z as shooting down. Again, it's all just perspective. But if this is what they're giving us, well, that means that my x value it's a length of 2 wherever my x is. It's a length of 3 wherever my y is, so I'm going shooting out 3 on the y. And then I'm going 5 units on the z. In this case, z is going up, so I'm going up 5 on the z, which, again, the sum of unit vectors, if you're going this way, and then this way, and then this way, well, that's how the sum is the shortcut. So if I'm going here, plus here, plus here, the shortcut up to the top is my new vector. And that would be written as 2 times I plus 3 times j plus 5 times k. You're just adding up those unit vectors. How about them apples? Vectors in 3-dimensional space. Do not forget the power of a video. If you missed anything or needed to re-watch anything, just go ahead. You can rewind, pause, yada, yada, yada. All right, well, what are we going to work on tomorrow in class? Now, right here is vectors in 3-dimensional space. We do have a quiz coming up, but I am not going to give that to you tomorrow in class. Okay, we're going to save that for the next class day. Tomorrow, I want to focus first on the practice handout. Get ready for that. Copy this in your notes. See you then.